In 2023 and 2024, the AI infrastructure conversation was dominated by training. How do we get enough GPUs to train frontier models? How do we scale distributed systems across thousands of nodes? But in 2026, the bottleneck has shifted. Interference is now the constraint that matters most. Welcome to the video. I am Anirban. I work closely with large-scale backend systems and LLM orchestration at scale. In this video, we'll explore how LLM serving architecture is evolving in response to GPU scarcity, production workload patterns. This is not about fine-tuning on prompt engineering. This is about the infrastructure layer keeps models available fast and cost-effective at scale. Traditional serving was simple. Deploy a model on a GPU, expose an endpoint, handle requests subsequently or in small batches. It worked at simple scale but couldn't handle production load. Continuous batching engines like vLLM and TGI changed this. They dynamically group arriving requests into efficient batches and stream responses as tokens generate. GPU utilization improved dramatically, no more idle time between requests, but it added complexity, shared KV cache and memory management, and long request blocking others. The current frontier is multi-clustered and decentralized fabrics. Instead of single clusters, inference spread across regions, clouds, or peer-to-peer GPU networks. This isn't just about redundancy, it's about accessing latent capacity in a supply-constrained market. A centralized serving architecture means you control a fixed GPU pool in one or more data centers, typically within a single cloud provider. The advantages are clear: predictable latency with compute in known locations, simpler operations with one stack and deployment pipeline, easier debugging with centralized logs and metrics. But the constraints are also clear. We have limited buyout GPU supply, distant users experience higher latency, provider outages kill your capacity, and demand spikes throttling or queuing. For most production systems, this remains the right choice. Centralized serving is operationally mature and well understood tooling and predictable failure modes. But decentralized architecture become compelling for workloads requiring diversity, GPU access beyond any single provider's capacity, or censorship resistance. Decentralized inference distributes serving capacity across independent nodes, different clouds, countries, or even consumer hardware connected peer-to-peer. Projects like Decentralized GPT and Deepin GPU networks pursue this model. The value proposition access latent capacity in idle GPUs across university labs, gaming rigs, and regional data centers. The architectural challenge is routing and trust. Unlike centralized systems, where you control the stack, decentralized nodes without run wrong model versions, inject malicious outputs, or fail unpredictably. This demands new requirement: verifiable inference with cryptographic proofs, reputation systems to filter unreliable nodes, and economic incentives rewarding uptime while penalizing failures. For public non-sensitive workloads, chatbots, content generation, research tools, this may be acceptable. For regulated research or industries or security critical applications, it likely isn't. Whether you run centralized or decentralized serving, certain scheduling or memory techniques are now standard in production-grade systems. Continuous batching is table stakes. If your serving engine is not dynamically batching requests, you are wasting GPU cycles. KV cache offloading is the next optimization. The key value cache from the attention mechanism grows linearly with sequence length. For long context or high concurrency, the cache can exceed GPU memory. Offloading it to CPU memory or even SSD allows you to serve more requests concurrently at cost of slower cache access. LoRA aware scheduling is relevant if you serve multiple fine-tuned adapters on top of a shared base model. The scheduler can swap adapters in and out of GPU memory efficiently, allowing you to serve hundreds of fine-tuned variants without loading separate copies of the base model. Scale to zero is critical for most control. If a model receives no request for several minutes, the serving engine can unload it from GPU memory entirely. When the next request arrives, the engine reloads the model. This trades cold start latency for reduced idle cost. These techniques include your API design and SLOs. Continuous batching means response latency varies with batch size and request mix. KV cache offloading means tail latency increases for long context requests. Scale to zero means occasionally cold starts that can take seconds. You cannot promise a fixed P99 latency without understanding how your serving engine schedules and batches work internally. GPU scarcity is structural, not temporal. AI compute demand outages supply. NVIDIA's rack scale systems like Rubin shift the deployment unit from individual nodes to entire rack with custom interconnect. This reshapes architecture. Buying a Rubin rack lock you into specific configuration for years. You can't scale by adding GPUs. Capacity planning shifts from weeks to quarters or years. This drives aggressive quantization. Running models in a 8-bit or 4-bit reduces memory footprints and enables more requests per GPU. Quality degrades, but for many applications, cost saving justify the trade-off. It also drives hierarchical serving tiers. On-device interference handles latency critical and offline use cases. Near-edge interference serves regional users with lower latency. Core inference runs in hyperscale clusters for highest throughput and demanding work. Policy-driven routing becomes essential. Sensitive data stays in compliant infra. Latency-sensitive workloads route to nearest capacity. Bulk low-priority workloads route to cheaper or decentralized compute. This isn't computation. It's a requirement when GPU supply is constrained and workload diversity is high. Inference is now the primary bottleneck in the production AI. Serving architecture has evolved through 3 stages: single instance deployments, continuous batching engines, and multi-cluster fabrics, each adding capability and complexity. Advanced scheduling techniques like continuous batching, KV cache offloading, and LoRA ever scheduling are production standards that shape API design and cost. GPU scarcity is structural, forcing aggressive quantization, hierarchical serving tiers, and policy-driven routing. Decentralized inference unlocks capacity but introduces trust challenges absent in centralized systems. If you are building AI infra today, inference serving is where the hardest architectural problem live. Understanding these trade-offs isn't optional. That's it for this video. Thanks for watching.